Okay, so everyone should now have had sort of a tab at the top of the screen that says that recording has now started. So you should all see that, and that lets us know that we're currently recording. All right, I forgot to start the recording until a little bit later, so thank you for the reminder. And we're currently discussing the composite that we manufactured, which was this 090 laminate. So this particular sample is very similar to the one that I previously manufactured. This is a 0393, and we're discussing the. Okay. All right. So what results? All right. So what results then when we do this? We have this curved lamature that is stable in two configurations. We have one that's stable in this configuration, and then if I rotate it 90 degrees, I can put it into another stable configuration that has sort of this upward curvature. Okay, so you might even be able to hear when the laminate snaps through sort of its neutral condition. Okay, so I'm going to try to flutter it quite a bit and see if we can hear the flutter between the two different stable conditions. Okay. Okay, so that's the fluttering between the two stable conditions. One where we have sort of this curvature pointing down in one direction. So here the curvature sort of pointing down. And then if I rotate 90 degrees and put it into its other stable configuration, the curvature is now kind of rotating upwards. So hopefully we all kind of see that. All right, this is a phenomenon known as a bistable composite laminate. Stable in two different configurations because of the way that it was manufactured. All right, so people have written many articles on this. All right, so I'm going to show some cool little internet articles that I found about this. Let's see. Leads to papers that look like this. Morphing of bistable composite laminates using distributed piezoelectric actuators. All right, so pretty interesting title. And now that we've had a little bit of discussion on what it means to be bistable, meaning stable in two different configurations, people have tried to leverage this to make, let's say, a flapping structure, like a flapping wing, for instance. Okay, so here's sort of an exaggeration of what I just talked about. So kind of the figure here, figure A, is the laminate at 300 degrees F, or what it would have been 300 degrees F for us. The laminate, because of the coefficients of thermal expansion, is flat when it's manufactured. It solidifies in this flat condition because we have all of the pressure on it. Okay, it's only when we cool it down that the shrinking of the various layers tries to exaggerate and become stable in two different configurations. So you see the two different stable configurations that I'm kind of talking about would be sort of like this image here in B would be stable configuration number 1, and the image here in C would be stable configuration number 2. And you can sort of force the composite to actuate or snap through these two different configurations, which is kind of cool. And so it leads to papers like this where authors would slap onto this particular composite that they've manufactured. Just got to scroll down a little bit here. They would slap on what you see here in figure 7, some piezoelectric actuators. And what's going on there is that they're using piezoelectrics, which is an electronically actuated mechanical device, to sort of give enough force on the laminate to snap it through its two different configurations. So you can imagine if we activate one side of the laminate to pull it in one configuration, then turn that off and activate the other side of the laminate to pull it back to its other configuration, we could create sort of like a flapping structure where we activate one, it flaps one direction, activate the piezoelectrics on the bottom, and it flaps at the other configuration. So some people have made some crazy structures, and you can Google all sorts of interesting stuff where they're flapping between, you know, some two different configurations. And this might be useful for creating, let's say, a valve. It could be like a flapping wing to emulate like a bat wing, for instance. It could be activating flaps on an aircraft, for instance, if you normally don't have the piezoelectric materials activated, and then you activate them to put flaps on your structure, so on and so forth. So this composite that we manufactured, it looked seemingly innocuous, doing sort of this like 0, 0, 0, 0, 0, 90, 90, 90, 90, 90 sort of thing. It sort of looked rather innocuous, but in actuality, there's a lot of learning that can be done with this composite because there's different coefficients of thermal expansion in the different directions of the lamina. And it creates this composite that ends up being curved and actually has two stable configurations of curvature just because of the way that it cools down after the manufacturing process. So people identify this and they realize that, oh, maybe we can use this manufacturing procedure to create a laminate that we might be able to use in some flapping structure, some morphing structure. Okay, so a pretty cool little laminate that we manufactured, even though it didn't really look all that crazy interesting during the process. Okay, so that was kind of a long tangent, but you know, trying to deliver interesting content here in this electronic world, so doing my best. All right, so general questions for the audience. I went through a couple of things there where I was looking at writing on the notepad, where I was kind of showing some articles on the internet and showing my composite piece. Can I just get some general comments in the chat about how did everything go? Were you able to see everything? Was the writing okay? Those sorts of things. Ready, go. Yeah, go. Sometimes my microphone. Okay. I will make a note. Thank you. Microphone quality suspicious at times. Can't hear you when you turn your head and talk. All right, so talk to screen. Specifically when I went to the notepad. All right, here's what I'm going to do. I'm going to purchase a headset or get a headset so that I can talk through a mic regardless of where my head moves. How about that? Is that a good compromise? I think that's a good compromise. Yeah, okay. So I'll make a note here, get headset. I think that'll help with a lot of the microphone issues, okay? I think that is probably the best compromise. All right, so I'm gonna do that and I'll play around with that and see what I can do with that, okay? Okay. Any other comments that people want to make? I see a lot of thumbs up. That's good. It's weird. I'm like in this room by myself. I'm like talking to myself. It's very strange. Like, I don't know how those like internet people do it. If you're like on Twitch and like watch video gamers, it's like what they do all day long. It's just, it seems very like isolated, even though I'm here with like 15 other people. It's very strange. But okay. All right, enough, you know, espousing. But it'll be better, I promise. Okay. So the other thing I wanted to do was I wanted to quickly cover, just in PowerPoint, a review of the stuff that we talk about in 429. So if you have the lecture notes available to you, I'm going to start in on the lecture notes and probably go through maybe the first 6 or 7 slides. All right. Then starting on Wednesday, we'll get into sort of the new material, which is covering more depth on the classical lamination theory. Okay. So question regarding your composite. If we were to cool the composite quicker, could you prevent the curvature? That's a complicated question. There's problems that could arise when you cool very quickly because the epoxy inside of the composite has a very low coefficient of thermal expansion, and the fibers relatively have a high coefficient of thermal expansion. So if you cool very quickly, those carbon fibers will shrink very quickly relative to the epoxy, right? So what happens then is you actually get a lot of separation between the fibers and the epoxy if you cool very quickly. So generally, you would not have globally as much curvature because the carbon fiber would be actually fracturing away from the epoxy as the material here. Okay, so it's a good question, and we'll talk about that more when we get to the bistable laminates and residual stresses portion of the course, which is in like 2.5 or 3 weeks. And I have some really cool images that I took when I was in graduate school that show sort of the fracturing between the fibers and the epoxy because of their significantly different coefficients of thermal expansion. Okay, so if you cooled quickly, disaster is all I'm going to say. That's why there's usually very slow cool down when you manufacture composites like this. Recommended a controlled slow cool down. Okay, good question. All right, so I wanted to get on with the notes on classical lamination theory. So I'm going to pull up my PowerPoint slide notes for lecture number 1, which is the classical lamination theory. So I'm going to share my screen now and show those notes. And I'm going to keep it not in presenter mode, but in sort of like the general PowerPoint presentation. All right, so I'm going to pull those up now. And I will share my PowerPoint with you guys. So you should all now be able to see the review of classical lamination theory slides that I have. Okay, so here we're just going to review material that we should have seen in 429. Okay, and after this very brief review, I will consider you ready to do homework number 1 fully. Okay, even though you should have already been able to do it. All right, so a quick review on anisotropic materials, right? So composites are orthotropic, and we need multiple material constants to relate stress and strain through Hooke's law, right? So typically, you only need 2 material constants for an isotropic material, like your aluminum. So you need modulus and Poisson's ratio. But generally, if you have an anisotropic material, most generally, we need 81 material constants for that behavior. All right. However, we talked about materials that are Cauchy elastic, which is a little bit outside of the scope of the 429 class, and materials that obey conservation of angular momentum, which is basically every material. Then we simplify our stress tensor to 6 components, which is sigma 1 through sigma 6, representing the normal and shear stresses on a 3-dimensional body with sigma 1 through 6. And we can create for ourselves a 6x6 stiffness matrix that gives us only 36 material constants. However, if, again, we have the stiffness matrix being symmetric, that reduces to 21. So the 6 along the diagonal, and then the 15 that are contained above or below that. All right, so this is our general review of the stiffness. When we talked about reducing the material constants based on symmetry, we could reduce based on symmetric conditions for a variety of different materials. Firstly, if the material was generally orthotropic, as most composite materials, you get down to 13 constants. And then for transversely isotropic materials, which is like a single lamina with unidirectional fibers, you could get down to 5 constants. So things like E1, E2, G12, Nu12, and Nu23. Those would be 5 constants. Okay. And then generally, if materials are isotropic, meaning they have infinite planes of isotropy, then we could have only 2 material constants describing our heat, which is what you're traditionally familiar with in like your ME3005 class, where you talk about the modulus of elasticity, E, and Poisson's ratio, right? We made further reductions in this these stiffnesses for thin materials, right? So thin lamina and laminates, like we made with our little composite here, our bistable laminate. I'm holding it in my hand. We're going to assume plane stress conditions, right? So there are no Z components of the stress, meaning that sigma 3, sigma 4, sigma 5 are 0. That's what it means to be in plane stress. So we have no out of plane stress, and we have no shear stress, X, Z, and YZ. Then we can sort of simplify our 6x6 stiffness matrix into a 3x3 in-plane stiffness matrix called Q. This here now relates the stresses sigma 1, sigma 2, and sigma 6, which you might think of as like sigma x, sigma y, and tau xy, into this sort of 3x3 arrangement. We called Qij the 3x3 in-plane stiffness matrix, and then the inversion of that is S, which is the 3x3 in-plane compliance matrix. And that's always confusing, that S is the compliance and C is the stiffness matrix, which, you know, I didn't name it, so, you know, what do you do? Right. So, continuing. We are able to relate the compliance matrix to material properties using sort of mock experiments, let's say uniaxial tension in the one direction to relate compliance S11 to strain epsilon 1 through these material properties and show that our compliance matrix S can be written in terms of traditional engineering properties like E1, E2, nu 1, 2, and E1. Okay, so that's all good if our loading axis and our material axes are coincident, right? So typically we talk about the one direction, no musical jokes implied here, but the one direction, they're making a comeback, aren't they? I don't know. The one direction being the direction of the fibers, and the two direction being across the fibers. However, we want to discuss material properties that might not necessarily be in the one and the two direction, but might be off axis, like X and Y direction. So for that, we need to talk about stresses and strains, not in the one and two direction, but in some arbitrary XY coordinate system, which might be oriented at an angle of theta with our material coordinates 1 and 2. So we do that using our in-plane transformation matrices, which are 3x3 matrices that allow us to go from principal material coordinates 1 and 2 to some arbitrary coordinate system X and Y. Next, then, we can relate or transform what are the in-plane stiffness and compliance matrices, Q and S, into off-axis stiffness and compliance matrices, Q bar and S bar, using these particular transformations. So if we have stress and strain off-axis, which we would label as sigma x and epsilon x, these vectors here, we can transform sigma x and epsilon x back to sigma 1 and epsilon 1 using our transformation matrices, and then write our in-plane stiffness and in-plane compliance matrices Q in terms of these transformations. So we end up with Q bar as a function of transformation matrices and the original in-plane compliance and stiffness matrices Q and S. Okay. This results and finally leaves us with relationships between what would be engineering properties in our modified XY coordinate system, things like epsilon x, or sorry, EX, EY, new XY, new YX, so on and so forth, as we see here. And one interesting thing that results is this new engineering constant called shear coupling coefficients. The idea that if you hold on a laminate and it was not necessarily any direction of the fibers, you could induce shear by pulling on that laminate. And that's this idea of, you know, different directions have different resistance to the stress that you put on it. So when you pull on it or stress it in one direction, it might shear to compensate for the different strengths, stiffnesses in the different directions. Okay, so that's all the math that we sort of went over and talked about in 429. The very end, we then got into very basic lamination theory. And the two different classes I taught in the past, you know, I had 429 twice before. Some people went a little bit more in depth on lamination theory than not. But both of you had this general idea of lamination theory, so I'll talk about it now. In that we have this stacking sequence where we talk about how the lamina are stacked on top of themselves to create a laminate. And we describe the direction of the fibers in the unidirectional lamina relative to the general coordinate system using angular measurement, right? So if we have 8 layers of unidirectional material stacked on top of each other in the same orientation, we would say that that's the 0, 8 composite. And if we had some other layup that was like 0, 90, 45, plus 45, minus 45, etc., we could describe that layup using this general notation where we have square brackets and then the angular measurements of the individual layups described in that stacking. Right? So this allows us to describe how the laminate was created from the individual lamina by relating the directions of the fibers in the lamina to some global coordinate. Okay. Finally, we define some laminate terms. So things like where is the kth lamina. We put our coordinate system in the middle of the laminate stack and then said that the location of lamina K is at Z sub K, okay? And the lamina one below that is at location ZK minus 1, and so on and so on and so on, okay? So we can describe where each lamina is in the laminate given our global coordinate system XYZ centered at the middle of the stack, right? The full height of this lamina we defined as h. One last thing that we saw that was because the lamina may be oriented in different directions. If we pull on the laminate globally in, let's say, an x direction, we might have variations in the strain. And because that strain is continuous and each particular layer might have a different stiffness, have this discontinuous stress variation throughout the laminate. So this becomes very important when we start talking about laminate failure, because the stresses in the different laminates are different. So you have to analyze every single lamina when you start talking about failure of the laminates, because they all have different stress levels. Okay, so that's about where we left off. In both classes had that material. So I will pick it up on Wednesday, starting from the new material, which sort of describes how we talk about loads transferring to stresses on the piece, and how we then describe engineering properties of the laminate given the loads that we apply. Okay, so with the last couple of minutes here that we have class, I just wanted to make sure that the vocal is good and you can see the PowerPoint and you can understand me and all that sort of stuff. So the slides on Blackboard are missing 8 and 9 I just presented. Okay, I'll have to upload some new slides to Blackboard. Apologies for that. All right, so Blackboard slides update. Okay, I will do that. Apologies for that. Other comments or questions? If you're hesitant to talk in the chat, you can also feel free to email me. Okay? All right. So if there are no additional comments or concerns, you can feel free to log off, and I'll stay here a little while. If anybody else has any comments, I'll just keep this meeting open for a little while. And then right after this lecture, I will move to the office hours location if anybody wants to meet me there for discussion. Okay, thanks for coming. Thanks for helping me through some hiccups. I'll get a headset and hopefully we can make things a little better next time. Okay, thanks for coming.